Hello everyone. It's an honor to introduce our study, learning to extract transaction functions from requirements, an industrial case on financial software. First, I began the presentation with the background. In industrial practice, it is important to have a reliable cost estimation before software systems are actually built. One of the most popular approaches is function point analysis. In function point analysis (FPA), given a requirement, the functions are manually extracted from requirements. Then, the expert will determine the function type and calculate the function point based on the extracted functions. Specifically, the most challenging activity in FPA is extracting functions. Functions are the descriptive information. They are usually expressed as a verb phrase or noun phrase in requirements. In the figure, I give a requirements example. As a cashier, I wish I can receive every payment confirmation when I successfully scan customer Alipay's QR code, and the corresponding function is receive payment confirmation. I will use it as an example to illustrate why it is challenging. The first challenge is that far from the part-of-speech pattern. There are several studies to extract phrase using the part-of-speech patterns. They assume that the target phrase are consecutive words in requirement. Taking a function in the figures as an example, the words are not always consecutive in requirements. There is a word every, splitting the other words in the function. The approach based on the part-of-speech patterns will fail in this case. The second is the FPA rule-driven extractions. According to the FPA rules, functions only refer to the system functionalities. They are usually verb phrase or noun phrase in requirements. However, not all the verb phrase and noun phrase are functions. Like the given example, there are two verb phrases in the requirements. They are receive payment confirmations and scan customer Alipay's QR code. According to the FPA rules, the phrase scan customer Alipay's QR code just describes a user action rather than a function. Extracting more functions will lead to overestimated cost. Therefore, the approach without distinguishing abilities are not suitable for function extraction. Considering that our study is motivated by an industrial case, we further introduce the FPA practice in our industry partners, China Merchants Bank. CMB. CMB is one of the largest banks in China, whose business areas involve credit card management, wealth management products, and so on. Most of the software are transaction-oriented applications, which are well adapted to FPA-based cost estimations. In addition, CMB has utilized the FPA practice over 10 years. In CMB, the FPA process launches when user requirements are collected and documented, guided by the official manuals. Product management extract data functions and transaction functions from requirements. Here, data functions represent functionalities to meet the data storage requirements, and the transaction functions represent the elementary process that provide functionality to user, including external input (EI), external output (EO), and external query (EQ). Specifically, data functions are domain-specific entities, which are obviously mentioned in requirements. They are usually written in non-phrase, where transaction functions are highly summarized activities that are meaningful to user. They are usually written in verb plus non-phrase, such as add a new customer and change the customer details. Therefore, it will be more difficult to summarize the transaction functions than mark out date functions from requirements. Moreover, transaction functions take up a majority of all functions. In particular, the transaction functions account for 80% functions in CMB. Due to the FPA practice heavily relying on the human judgment, it is important to make sure that the manual results are correct. Therefore, when the product manager submits extracted functions, the expert will review their submissions and correct mistakes. Finally, the expert put a number of functions into the predefined formulations to calculate the adjusted function points and schedule using the function points. In this process, the function extraction is the most costly process, which involves a large amount of human efforts. Besides, the extraction is error-prone. According to the investigations, CMB suffer from the following issue in extracting results. The most common issue is using a part of individual elementary process as the transaction functions. For example, identify one step enter password rather than the entire process. User login. There are also other types of the issue, such as duplicate, missing functions, and so on. Therefore, it is important to propose approach to promote the automation's effectiveness and quality of function point analysis. Thus, we propose an approach to automate the transaction function extraction. In our approach, we first train a classifier to predict whether each word in requirements will appear in a function. Using the word predictors, it can distinguish which words are related to functions, which can overcome the challenge of FPA rule-driven extraction. Then, we construct functions by pattern-speech parsing and dependency parsing. According to the dependencies, we can overcome the challenge of far from the pattern-speech pattern. Finally, we train a classifier to predict function type. The figure gives the overview of the approach. First, we extract 6 categories of the features for each word in requirements based on the textual parsers, heuristic rules, word embedding models, and lexical graphs. Second, we train a word predictor with the requirements corpus and select the optimal one to predict words in function. Finally, we construct transaction functions by combining words, ranking by polarities, and classify the function type. The output of our approach is a list of the suggested transaction functions extracted from the requirements together with their function types. The following introduces the detail of each step. The first step is to extract the feature for each word. The features involve six categories, including term features, location features, frequency features, history features, representative features, and importance features. The details of each feature are shown in the table. There are totally 21 features used for the word predictor. Second, with the built features, we train a binary classifier to predict whether each word will appear in a function. The positive word will used as a keyword for the function construction. Third, with the predicted words, we construct transaction functions by a pipeline, including combining words, ranking by paralycities, and classify EI, EO, and EQ. The algorithm of the transaction functions construction is shown in the figure. When constructing transaction functions, we first combine the words. Considering that the transactions are the verb phrase in the form of the verb plus compound noun phrase, we implement combinations by pattern-speech parsing and dependency parsing. We first conduct pattern-speech parsing and dependency parsing. For example, there is a requirement: I would like to modify billing remainder time so that I can pay in time. The pattern-speech parsing result and the dependency parsing result are shown in the figure. And if a word time is predicted as true by the word predictor, we first retrieve the compound noun phrase billing remainder time according to the pattern speech type. Then, according to the dependency, we find that the billing remainder time is the direct object of the verb we modify. Therefore, we find the modified billing remainder time is the target transaction function. To suggest functions with good readabilities in high priorities for early review, we utilize an n-gram language model to rank the combat result. We rank all the extracted transaction functions by paralycities. In this step, we train a language model using the history transaction function. The trained language model could capture the regularities within the corpus. Using the trained language models, we can also calculate the paralycities, which can measure how well a function is in line with the history transaction function corpus. Then, we suggest a function with low paralycities in priorities. In the last step, we determine the three function types, EI, EO, and EQ, for each combat results. Four common text classification models are considered as a classifying function type. They are naive Bayes, logistic regressions, J48, and random forest. We use the TF-IDF method to represent each word in functions, in which the frequencies of the words are multiplied by their inverse documented frequency. We train these classifiers by transaction function corpus. We select the optimal one with the highest performance as the function type classifier. Then we introduce the evaluations. Our data is collected from the IT department in CMB. We collaborate with the project management department of the CMB and help them to increase the level of automations in software effort estimations, which can reduce the expensive labor costs and difficulties in applying FPA method. Our evaluation using the following two datasets: requirement functions corpus and transactions functions corpus. Specifically, requirement function corpus contains all the textual requirements and their corresponding transaction functions. Transaction function corpus contain all the history transaction functions. The details are shown in the table. Then we give the achieved results. To evaluate the effectiveness of the word predictor, we propose the research question 1. To what extent can the word predictor identify words in the transaction functions? We select a full supervised machine learning approach and use the tenfold cross validations on requirements function corpus to evaluate the performance. The figure shows the result. In summary, using the random forest algorithm, the overall accuracy could reach 94%, which indicates that the word predictor can effectively predict whether the words in a requirement will be included in its corresponding transaction functions or not. To evaluate the quality of the function content, we propose the research question 2. How effective is our approach in extracting transaction functions from requirements? In IQ2, we use the BLEU to measure the content quality of the extracted functions. The value of BLEU is in the range of 25 to 40. It's considered as a high quality. The result indicates that the extracted functions are in low velocities, which indicates that the high quality of the extracted functions. Then, if an extracted function's BLEU value is larger than 25, we consider it as a valid suggestion. Based on all the transaction functions extracted from each project, we find that most projects have more than 60% valid suggestions. To evaluate the correctness of the function type, we propose the research question 3. However, can our approach correctly classify the type of the transaction function? We use the four popular classified algorithm, and we use the two strategies to evaluate the performance. One is the tenfold cross validations on the transaction function corpus. The other is to train the full models on a 9-year transaction functions corpus from 2010 to 2018, and then test on the requirements functions corpus in 2019. The two tables show the evaluation results. From the result, we can find that on average, the random forest algorithm could achieve F1 score of 88%, 87%, or 99%, 97%, and 99% for EIU and EQ respectively. Finally, we conclude our study. In this study, we propose an automated solution to extract transaction functions from textual requirements. The practice shows that the deeper knowledge can be mined from the textual requirements by leveraging a set of advanced natural language processing techniques and machine learning models. Besides, our approach provided high-quality functions with accurate types, which can assist industrial partners to estimate size faster and easier. Thanks for your listening.